Now that we've seen how a two-cycle is born, let's look more precisely at the stability near the fixed points of the two-cycle. And here the algebra of iteration turns out to be our friend and makes the evaluation of the derivatives of f of x actually very simple. So let's imagine that we're at the two-cycle, and let's look at the slopes of the second iterate function at the fixed points. So as we've seen on a two-cycle, there's two sets of fixed points. There is the unstable fixed point for the first iterate function, and then there are the fixed points of the second iterate function. And we would like to think that the second iterate function, the fixed points are stable, and the first iterate, the fixed points are unstable. So let's look at the slope of f2 of x at the fixed points. So we want to compute the derivative of the second iterate. And here we just use the chain rule of calculus, because this is nothing more than f of x, the derivative of that, and this is equal to, by the chain rule of calculus, is f prime evaluated at f of x, and then times the derivative of the argument, and so that's equal to f prime of x. So if we're at the fixed point of the first iterate, and the fixed point is defined by x star is equal to f of x star. Inside the argument of the first derivative, f of x at x star is equal to x star, and so this quantity here is equal to f prime of x star, and the second derivative is f of x star yet again, and so this is nothing more than f prime of x star quantity squared. So if there is a stable two-cycle, that means that the fixed point of the first iterate function is unstable. If we start close to there, we're driven towards a two-cycle, which means that the derivative of the first iterate function is greater than 1. And so when I square it, this is certainly greater than 1. And so that means that the function is unstable. The second iterate function is unstable at the fixed point. At the stable points of the second iterate function, and so these stable points were either what we called xa or xb. So let's again evaluate the derivative at either xa or xb. So let's look, for example, at f2 of xa, its derivative. And again, applying just the chain rule of calculus, this is nothing more than f of xa, derivative, all that. And so this is equal to f prime of f of xa times f prime of xa. But by the definition of a two-cycle, if I'm at point xa, then after one iterate, I move to xb. And so this is equal to f prime of xb, because f of xa is xb, times f prime of xa. And so this is symmetric in the interchange of a and b, and so this clearly is the same as f2 of xb prime, the derivative of the second iterate function at xb. So the point is that at the birth of a two-cycle, first of all, f2 of xa equals f2 of xb. And you can see graphically that right at the birth of the two-cycle, these two slopes are equal to 1. And these slopes decrease continuously as I increase the control parameter a. So these decrease to -1 when a reaches a critical value, which is approximately equal to 3.46 ... When this happens, these fixed points of the second iterate function become unstable. That is, that xa and xb become unstable. And this gives rise to the birth of a four-cycle. And this procedure continues on and on ad infinitum. The point here is that when I have instability of the fixed point of the first iterate function, we had single hump function and the slope of the fixed point became less than -1. And we saw then that that gave rise to a birth of a two-cycle. And if I looked at the second iterate function, that had two humps. There were two equivalent points that had slopes that started off at +1 and then approached -1. And at each one of the humps, the same phenomenology in the second iterate function occurs as in the first iterate function. So going from a one-cycle to a two-cycle, that phenomenology is the same as two-cycle going to a four-cycle at a smaller scale. And this series of period doubling bifurcations continues on and on until we can have basically an infinite number of period doubling bifurcations.